So I'm going to have two other videos on IMFs. The first one's going to deal with the weakest IMF, which sometimes can be large because everything overlaps here. It's not very as simple as it was once presented. And the IMF I'm going to focus on is called London dispersion forces. Now, London dispersion forces are due to temporary, asymmetric distributions of electrons slash charge. Excuse me. So imagine you have a single atom of neon here, and you have another molecule of neon. Well, these are both nonpolar molecules. However, this nonpolar molecule is capable of sticking to the other nonpolar molecule, and it has to be a reason. Supposedly, they're both neutral, so they shouldn't attract each other, but yet you can liquefy neon, just like you can liquefy any nonpolar substance. Now, the London dispersion forces, and I'm going to emphasize this by saying it loud and quite and two or three times, occur in all molecules, every single molecule. However, for nonpolar molecules, they are the only IMF that they have. They don't have other ones like dipole-dipole interactions and hydrogen bonds. So London dispersion forces are found in all molecules, and the concept is pretty simple, right? If you have a molecule and it's got all these electrons that are zooming around, right? At some point, there might be more electrons on one side of the molecule than the other. That causes that molecule to have a partial negative on one side, and the other side ends up being partial positive. Now, they say all these molecules are polarizable, and that this polarity, where you have a positive side and negative side, is inducible. These are really important terms to know. So if this side is negative for just a moment, because it's a temporary asymmetric distribution of electrons or charge, then an adjacent molecule can be induced and become polarized. And the one doing the inducing will be molecule A. So molecule A has a dipole. It's temporary. Since it's negative on this side, it will push the electrons in the adjacent molecule are moving all over the place. However, because this is negative here, it will push the electrons in this side over here, over to here, and so the electrons will end up over here because they will be repelled by the negative, and they'll end up over here. And so this side will become negative in that molecule, and this side will become positive in this molecule. So molecule B will have its poles on opposite sides. And because the two molecules are adjacent to each other, they will then stick to each other. And that's really what London dispersion forces are. Molecule A induces a dipole in molecule B by pushing away the electrons in the adjacent molecule. Now, there are three variables that affect the strength of these London dispersion forces. The first one is implied in what a London dispersion force is, and that is distance. Now, just like gravity, anything that involves Coulombic forces, which is just a big word for charge, are affected by distance. I don't feel the gravitational pull of Jupiter very often, but I do feel the gravitational pull of Earth because I'm not flying by myself. So distance plays a role. General rule is, okay, if they are closer, then they are going to be stronger. And that will affect another variable I'm going to talk about in a moment. Now, the second variable has to do with the molecular weight, but really the number of electrons. So if you're dealing with, let's say, the halogens, and they're a great example because they have different melting points. So the melting point for fluorine is negative 220 degrees Celsius. The melting point for chlorine is negative 101. And you should know they're low because these guys are both gases at room temperature, which means they must boil at very low temperatures, well below room temperature. Bromine, which is a liquid, has a melting point of negative 7.2 degrees Celsius. So negative 7.2 degrees Celsius, bromine will turn from a solid to a liquid. So by the time it gets to our room temperature, which is like 25 degrees Celsius, it is a liquid. It boils at about 58 degrees. So if you get up to 58 Celsius, then the bromine will actually turn to a gas. And iodine melts at 114 degrees Celsius. Now what you're seeing a general pattern. As you go down the column, the melting points turn into larger and larger values, and so do the boiling points. Because as you go down the column, the strength of this particular IMF increases. Now, the only IMF these guys have, and the reason why I'm using them as an example, is because they are clearly symmetrical nonpolar molecules. So I can compare, say, F2 and Cl2 both have very similar structures. They're both two diatomic molecules. They're both nonpolar, and the IMFs are increasing. Now, why are they increasing? Well, the general rule is if you have more electrons and your structure is the same, things with more electrons are more polarizable. And the actual partial charges will be greater. Those partial things are not meaningless. They're actually you can look them up and find numeric values for them, right? So, like if you have an ion, like sodium is +1. Well, what is the partial negative on the side over here and the partial positive over here? Well, this is something between 0 and up to -1. It's closer to 0, but it's a negative value. It's actual numeric value. If you have more electrons, actual value of the negative charge will be a greater negative value. It will be closer to -1 and further from 0. Same for the positive charge. So if you have more electrons, you're more polarizable, and the actual numeric value of your partial charge will generally be greater because you have more electrons that can get displaced, giving you a larger negative or positive charge on the two sides. Now, the third variable, and this is true for anything, like so if you go down the noble gas column, which are monatomic molecules, as you go down the noble gases from helium down to like xenon or radon, whatever, the melting points and boiling points are going to increase as well because they have more electrons and therefore they are more polarizable, and the partial charges will be greater values. Okay, so you can look at other similar molecules. So I've got a bunch of tetrahedral symmetric molecules. And this one right here has the largest molecular weight of the four, and therefore this one will have the highest melting point and the highest boiling point. Now, the other thing has to do with the shape of molecules. Partly you can think of this as how close can the molecules get to each other, right? So if you have a molecule that's linear, right, it can get closer to another molecule. Things that have lots of branches tend to not stick as well. So if you have two linear, like these are both these are called N-pentane. Straight chain molecules can align right next to each other, and because they have more places where they can interact, they can cause more of these temporary dipoles. So if you had a 5-carbon molecule that was straight versus one that's branchy, the one that's branchy, since this other one, if I draw another one next to it, it really can't get very close to the other one because of the branches. And therefore, since there's less places where it can actually interact or get close to the other molecule, the IMFs are weaker. So if they can get close to each other, they can induce more dipoles, and so they will be stronger. Now, this plays out in a classic biology example, which is saturated versus unsaturated fats. Now, saturated fats are things like butter, margarine, lard, yuck, okay? All of which are solids at room temperature. And because they're solids, we can assume that their IMFs are greater than things like corn oil or canola oil or peanut oil and things like that, or olive oil. Well, what's different about them? Well, the corn oil and the other things these guys are unsaturated. And what that means is this: a saturated fat like the one on the top here, now really this is not a fat, this is a piece of a fat. Usually it's the molecule is larger, it's what's called a fatty acid. It contains a glycerol on 3 of these hydrocarbon chains. But if it's saturated, all the bonds in these chains are single bonds. And what that means is around every carbon, it's tetrahedral. And what they do is they arrange themselves like this. The carbons here, the 2 hydrogens here, the carbons here, the 2 hydrogens are here. The carbons here, the 2 hydrogens are here. And the carbons kind of make this zigzag thingy in a straight line like this. Unsaturated fats, on the other hand, have at least one of these double bonds. And what that does, it causes almost like a kink in the chain. And what that means is if I have another one that right here, it can't line up right next to it. It can't get close to it. And what that means is in order to turn corn oil into a solid, since the IMFs are weaker, you have to get to a lower temperature. So unsaturated fats okay, have a lower melting point and lower boiling point than saturated fats because the molecules are not able to get as close to each other. They're not allowed to pack as tightly, and therefore they're not allowed. And by the way, these are all considered nonpolar molecules. Anything that's like one of these organic hydrocarbons are considered nonpolar for the most part. It's a relative term. But for nonpolar fatty acid chains, the ones that are saturated can get closer to each other, and so they can be constantly inducing these temporary asymmetric distributions of electrons, and they'll stick more, and that means that they are solid at room temperature, and they melt and boil at a higher temperature.